Good morning, everyone. This is Bhavyashree from CSITA section. Today, my tech talk topic is about neural network pruning techniques for model comprehension. Introduction to neural network pruning. Neural network pruning involves removing unnecessary parameters to reduce model size. It aims to improve computational efficiency without significantly sacrificing accuracy. Pruning techniques are essential for deploying models on source constrained devices. The next slide is about motivation for model comprehension. Large neural networks require high memory and computing power. Model comprehension enables deployment on edge devices with limited resources. Pruning helps in reducing interference, time, and energy consumption. The next slide is about pruning techniques. Pruning methods can be categorized as structured or unstructured. Structured pruning removes entire neurons, filters, and channels. Unstructured pruning removes individual weights based on importance criteria. How pruning works. Network evaluate importance of neurons, remove the least important neuron, fine tuning, continue pruning. If yes, you will go to the second step, evaluate importance of neurons. If no, stop pruning. So this is the way pruning works, the process of pruning. Unstructured pruning overview. Unstructured pruning eliminates weights with minimal contribution to outputs. It results in sparse weight matrices where can be stored efficiently. This technique offers high comprehension rates but may require sparse matrix computations. The next slide is about structured pruning overview. Structured pruning removes entire structure like filters or neurons. It maintains the regularity of the network, facilitating faster computation. This approach often leads to more hardware-friendly models. Here is the difference of unstructured pruning and structured pruning. Magnitude-based pruning. Magnitude-based pruning removes weights with the smallest absolute values. It is simple to implement and computationally inexpensive. This method assumes smaller weights contribute less to the model's output. Gradient-based pruning. Gradient-based pruning considers the importance of weights based on gradients. It removes weights that have minimal impact on the loss function. This method can adaptively identify crucial parameters during training. The next part is about iterative pruning and retraining. Pruning is often performed iteratively with retraining after each step. Pruning is a process of iteration. This process helps the model recover accuracy lost due to pruning. Iterative pruning helps in retraining the lost models in pruning. Iterative methods typically yield better comprehension accuracy trades-off. The best method in the pruning is iterative pruning and retraining. Pruning during training versus post-training. Pruning can be integrated during training or applied after training completion. Training aware pruning can lead to more effective, efficient models from the start. Post-training pruning is simpler but may require fine-tuning to regain accuracy. The next slide is about lottery ticket hypothesis. The lottery ticket hypothesis suggests sparse subnetworks can train as well as full models. Identifying these subnetworks involves pruning and refining weights. This concept emphasizes the importance of initialization and pruning strategies. Here is example the lottery ticket hypothesis finding sparse trainable neural networks. Regularization techniques to aid pruning. Regularization models like L1 encourage sparsity in weights. These techniques make pruning more effective by promoting smaller weights. Combining regulations with pruning improves model comprehension results. The next slide is about hardware friendly pruning. Structured pruning produces models suitable for efficient hardware implementation. It reduces irregular memory access patterns typical in unstructured pruning. Hardware pruning considers device specific constraints for optimal results. The next slide is about pruning challenges and limitations. Excessive pruning can lead to significant accuracy degradation. Determining the optimal pruning ratio remains a challenge. Pruning method may require extensive computation and tuning. The next slide is about evaluation matrices for pruning. Model accuracy and comprehension ratio are primary evaluation matrices. Inference speed and energy efficiency are also crucial. Maintaining a balance between comprehension and accuracy is essential. The next slide is about practical applications of pruned models. Pruned models are used in mobile applications and IoT devices. They facilitate real-time interface with limited hard work. Pruning enhances the deployment of deep learning in embedded systems. The next slide is about recent advances in pruning techniques. Automated pruning uses reinforcement learning, a neural architecture such is emerging. Dynamic pruning adjusts the network system during interference. Combining pruning with quantization offers further model comprehension. Broadcast oriented VT pruning. Future directions in neural network pruning. Developing pruning algorithms that adapt during training continues to be an active area. Integrating pruning with other comprehension techniques can yield better results. Enhancing hardware pruning for specialized accelerators remain a priority. Summary of key points of this PPT. Neural network pruning effectively reduces model size and computational requirements. Both structured and unstructured pruning have distinct advantages and challenges. Combining pruning techniques with other comprehension models can maximize efficiency. So hereby we come to the conclusion of this PPT. Conclusion. Pruning is a vital tool for deploying neural networks in real-world scenarios. Ongoing research aims to improve pruning strategies while maintaining accuracy. The future of model comprehension involves intelligent adaptive pruning methods. So here we came to the conclusion. Let's go through the topics we learn in this PPT. The topic number one is to introduction to neural network pruning, and next motivation for model comprehension, types of pruning techniques and the process of pruning, unstructured pruning overview, structured pruning overview, magnitude based pruning, gradient based pruning, iterative pruning and retraining, Pruning during training versus post training, lottery ticket hypothesis, regulations, techniques to aid pruning, hardware friendly pruning challenges and limitations, evaluation matrices for pruning, practical applications for pruned models, recent advances in pruning techniques, future directions in neural network pruning, summary of key points of the PDF, and conclusion of this PDF. So, hereby we came to the conclusion, and that's it for the topic neural network pruning techniques for model comprehension. Thank you.